Thank you, Peter, for your introduction. It was certainly unfortunate that last year I couldn't deliver my speech as recipient of the Krumbein Medal, but well, we all know what happened and which is the situation that we are right now. And I thank the association for giving me the opportunity to give this talk and also to take the advantage to thank the association for the medal and also to thank everybody who has helped me during my career and has allowed me to reach this major milestone in it. Thanks to my mentors, to my advisors, my colleagues, my PhD students, and certainly my wife who has been behind me, all these years. The title of this talk is A History of Contaminant Source Identification in Aquifers, and I mention it's short because it's only 40 years long. It's only 40 years ago that the first paper on this subject was published. And I hope that even though it sounds that it's going to be very specific, you will see, many different approaches to solve inverse problems and identification problems and optimization problems, and that also that you may, some of you may share the frustration that has led me to write, to deliver this speech and to get this deep into this review about contaminant source identification. A frustration of the difficulties on the application of stochastic approaches in hydrogeology in general and to contaminant source identification in particular. I will give you a spoiler. At the end of these 40 years, I feel that we have focused too much on the solution of a mathematical problem that is well posed, well stated, but forgetting the fact that we are mathematical geoscientists and we want to apply this into the geoscience, into real application to solve real problems. And my feeling is that we are still too far from being able to apply these approaches into forensic hydrogeology. The statement of the problem is very simple. It was posed by Stephen Gorelick 40 years ago in his PhD at Stanford. And basically, you can see here on the right an aquifer discretizing a few cells. The water in the aquifer is moving from the top to the bottom. And there is some pipe leaking on it that it has two pieces broken at locations 3 and 8. That leakage basically introduced some contamination into the aquifer, which is monitored, which is discovered into these monitoring locations labeled S1 to S8. The question is, can we identify the locations where the pipe broke, knowing which, the history of the contamination evolution at those observation locations? That's the statement is very simple. It's clear, and as you will see, it has been the subject of research, of active research for the next 40 years, with an exponential increase in the last few years. The problem is none other than an inverse problem. We have a forward model that if we know everything about the aquifer, where the injections happens, everything, we can predict where the concentrations will appear, how the contamination will evolve in the aquifer. And basically, we want to solve the opposite. No? We want to find out, knowing which have been the contaminations, try to find out which were the locations and the strengths with which the contamination entered into the aquifer. For the specific case that Stephen Gorelick addressed, you can understand that the forward problem is linear, is basically just a linear convolution in which you can compute the concentration at any location ij in your aquifer at any time t as a convolution of the response of the aquifer to a unit pulse at those locations where the contamination may enter. Okay, so basically you have this linear combination where alpha kt are these pulse responses, what happened at as a response due to an injection in that location K at time T, how this is going to affect the concentration, the contamination at location IJ. And the only thing we have to find out are the strengths that we have at any and all of those potential leaking positions. So it's a very simple linear problem. I mean, we have to find that this CK, given that we know some of the CIJT, I mean, we know some concentrations. And the way Gorelick solved it, he applied two different approaches. Yes, basically linear programming, trying to minimize the absolute deviation between predictions and observations, and also least square approach, minimizing the quadratic deviation between predictions and observations. The notation I will be using, although I will not be using too many equations on the presentation, is the one presented by Tarantola many years ago, in which basically we have a forward model in which the state of the system D, in this case the concentrations, are a response, are a consequence of a forward model on the parameters M, and in this case the M parameters are basically this concentration source information, the strengths of the contaminant that enters into the aquifer, the history of how it enters. What we are trying to minimize is some objective functions that is a weighted sum of the differences between the observations and the predictions, this dcal, to some power p. That could be 1 if it's linear. I mean, we are looking at linear deviations, so it could be 2 if it's a quadratic deviations. And since the decal, the calculated conductivities, are obtained using an observation operator into the state of the system that is directly related to the with the parameters that describe the system through the forward model G, then we can see that this objective function depends on those parameters, and we can do just an optimization approach to find which are those M parameters. The limitations of this specific paper by Steve Gorelick was that you need to know where the sources could be. I mean, it was not trying to find just an unknown location of the leakage. I mean, you knew that the leakage is coming from the pipe, and you know that which could be in this particular case the cells in your discretized aquifer where the source could happen. And also in this case, the release history was known in the sense that it was a continuous injections. Once the leakage happens, it's continuously injecting to the aquifer. The aquifer is also perfectly known, including boundary conditions and external stresses, something that is not going to happen never, except for the leaks, information about the leaking, which is the one that we are trying to identify. And all the processes are also known. I mean, in this case, it is non-reactive transport. I mean, we assume that we know exactly which are the processes that are being known. Therefore, our forward model is exact. I mean, it really relates the state of the system with the model parameters, because we know perfectly which are those processes. Here you have the number of papers published since 1981. And you can see that there was basically, I mean, not too many publications in the first, I would say, 20 years. But then the last 20 years, there has been this surge of publications with more than 13, 14 papers published every year in the last few years. If you look at this histogram in cumulative form, you see that there is kind of an exponential increase on the number of papers published on the subject, especially on the later years, with the first 20 years, as I mentioned, going up to 30, 35 papers at most. This is a timeline of the publications. Here you have all the papers that have been published in this cumulative histogram, would be this blue figure that is seen on the left. And then I have marked in this timeline those years in which I think there were some breakthrough publications that certainly made an advance on the solution of the problem. And I will discuss some of them in the next slides. those years which are in white is because there was no paper published. So at the beginning, as you can see, the number of publications from the first paper by Gorelick to the next one, which made really a breakthrough. I mean, it was almost 10 years that passed between them. As I said, the next important paper that came out was this paper by Bagtsoglu and others. That it approaches the problem with a very different framework, which is it's based on this backward probability simulation. There is a framework for modeling transport in heterogeneous media, in which you can relate the concentration of the solute. It can be identified with the probability that a particle which is released at location x0 reaches location x. Okay, so you can compute, I mean, which are the potential trajectories that a particle may follow in an aquifer that is heterogeneous, and you can relate, as I said, the probability that the particle goes from x to y with the concentration that you will have at the end point location. So the idea of Bagtsoglu was if I am already in the end point, and then I have my concentrations at some time after the leakage, then I could go backwards in the same way that my concentrations were associated with the probabilities. I can go backwards, and the simulation of the backward concentration will identify me in the locations where the injection happened. And I show you this with this image taken from their paper. On the left side, you see which is the situation, say at time t, after time 0, where time 0 is the instant where the injection happened. So I have this injection, and I know now time t, which is the distribution of my concentration. Then what I'm going to do is running a transport code, but backward in time. And what I get is what you see on the right side. And now what you will have to do is to interpret those contour lines as probabilities that of the location of the injection. You need to know exactly when to stop. I mean, you need to know exactly when the injection happened. That's information required. But if you have that information, this backward simulation can identify, in this case, the 3 locations where the injection happened and produced the plume that you see on the left side. This backward probability approach was certainly a new way to look at the problem, and also they demonstrated accounting for heterogeneity of the conductivities that had not been accounted before. Next, in 1992, Brian Wagner, a student of Stephen Gorelick, proposed something that it's important because for the first time we realize that there is a need to identify not only the contaminant source but also the conductivities of the aquifer. I mean, you don't know the aquifer properties, therefore you need to account for that information. You need to try to identify also the heterogeneity of the aquifer. The problem is that, as you can see here, the formulation of the problem is very simple. The heterogeneity is only just 2 zones of known geometry with different values for the conductivity. And what Wagner identifies in this case are the strengths of the source in the injection location, where the injection is known and the injection time is also known. And what it will have is some observations both of head, of the piezometric head, and of the concentrations to identify jointly both the parameters that describe the flow and transport in the aquifer, and also the source parameters, the parameters that describe the contaminant source. It's the right move, but in this case was a too simplistic representation of heterogeneity. In 1994, there is another step forward, in that for the first time there is this paper by Skaggs and Kavala that tries to reconstruct an time-varying injection. Up to now, it was either continuous injection or pulse injection, or if there were several injections, were fixed in some few number of injection stresses periods. In this case, no. In this case, it's a continuous function, injection function, and the objective of the paper was to try to reconstruct this. The way they did it was by basically discretizing this function in many points, in many small locations, and trying to identify the concentration for each instant in this release location, release function. Because the problem, this inverse problem will becomes an ill-posed problem. I mean, there are too many locations, I mean, too many unknowns to identify. There is a need to introduce some regularization term. So the objective function includes not only the deviation between observations and predictions, but also this term here, which is a regularization that will induce some properties to the final function that it's being estimated. In this particular case, the authors proposed the use of the Tikhonov regularization, that basically what will prevent is rapid fluctuations of the values of the concentration from one time to the next. So at the end, you get something which is a relatively smooth curve and alleviates the problem of the ill-posedness given by the fact that you have many unknowns to identify. This approach certainly added some complexity to the problem that had been posed so far, but it was a one-dimensional solution. So it was solved only on a one-dimensional aquifer. In 1996, Goodbury and Ulrich proposed the use of this minimum relative entropy, and the main interest of this proposal is that they shift from a deterministic analysis into an stochastic one. The parameters are considered now random variables, and the optimization, what seeks is to find out the parameter probability distribution functions which are consistent with the observations. And what does this consistency mean? Basically, what they minimize is this relative entropy function that you see here, that relates both the posterior distribution, which is the one that we are seeking, and the prior distribution. You need to have some prior information about what could be the distribution of your parameters, and they minimize this this equation subject to a number of constraints, in which basically what they say is that the expected value of basically the transformation through this forward model G of my posterior distribution matches my observations. Okay, so what I'm doing is basically, as I said, I am matching some moments of my posterior distribution using my observed data. This can be done easily when the model is linear, because then you can interchange the forward model and the probability and the expectations easily, and can be postulated, as I mentioned, in an easy way. However, what they solve is the same problem as SCACs, that is a one-dimensional problem with a time-varying function, and in this case, as in the case of SCACs, the location is not subject to identification. It's just to try to identify the time function that has injected the concentration in the aquifer. In 1996, we get the first heuristic approach that shows up in the solution. I mean, so far we have seen most of the approaches have been simulation optimization approaches. We have this objective function that we want to optimize. Then at Allen 1 see that maybe we can try to use some of these new heuristic approaches to solve the optimization problem to reach a better solution. And they propose to use the use of genetic algorithms. And I would say that they still, what they use is the same problem, very similar to the problem as the problem of Gorelick, in which basically you have most of the information about the aquifer is known, and you are only trying to identify a few parameters in there. In 1997, we get the paper by Snodgrass and Kitanidis, which they introduced the application of the geostatistical approach to the identification of a contaminant source in an aquifer. Basically, what they frame the problem in a stochastic setting, and assume that the release function will be a realization from a multi-Gaussian random function. And what they are going to do is that taking advantage that the relationship between the observations and the parameters is linear, you can compute the cross covariance between parameters and observations, and basically do a co-kriging of your in this case your injection function. They do this. They address the same problem as SCAGs, and they try to fit this time varying function. On the right side, what you see is one of the solutions in which you have the reference function, and then you have some kind of dashed lines showing the estimated value with some confidence intervals of the estimation. What you can see here is that because you are doing kriging, and kriging doesn't enforce nonlinearity, in those areas where the concentration should be 0, the estimation at in some cases gives values which are negative, which are certainly non-realistic. This first application, is still one-dimensional. It's still too focused on the source problem, disregarding other uncertainties about parameters or stresses. And in this particular case, the authors emphasize the fact that they not only do the estimation of the injection function, but they also estimate the hyperparameters of the basically the covariance function and the mean that is using this multi-Gaussian random function setting to describe the injection function. As I mentioned, since kriging cannot enforce non-negativity, the authors also propose a transformation rather than to work with concentration, to work with a transformation of the concentration, so that and do the estimation of this transform variable, so that when we back transform, you ensure that there is no values which are negative. The problem is that this transformation renders the relationship between parameters and observations nonlinear, and then the calculation of the cross covariances is not exact. So they have to do some additional work, some iterative work to try to basically solve that problem. In this case, as I said, in an iterative way. In 1998, there is the first application of three-dimensional approach. I mean, this Goodwoody and others basically continue with their approach, with their demonstration of the minimum relative entropy that they had developed before, and they applied to a three-dimensional case, but using as a forward model some analytical solutions, which again yielded a little bit far from being applicable really to real sites, although they do demonstrate it with an application into a real site, and basically they say that their application reduces the uncertainty bounds that they had prior to apply this approach. So we have reached 1998. I'm showing you again the timeline. You see, I mean, from 1981 to 1998, there are about 30 papers published. There are many papers publishing different changes that try to get better solution of the problem, and then we will run. Then we will have a number of years basically dry with papers that represent only incremental research with respect to what has been published before, and with very few new approaches, new contributions to the solution, to the real solution and application of the problem to practical cases. In 2004, we have the first application of artificial neural networks. This century is the century of artificial intelligence and machine learning, and it was clear that they had to come into play. There will be many papers using machine learning and artificial neural networks that will come afterwards, but this was the first one. In which Singh and Datta and Jain they train a network, just basically to identify identify the locations and the strengths in some locations. They also do an identification of the parameters of the aquifer. They assume that the aquifer is homogeneous, but with unknown conductivity and unknown porosity, and also with unknown longitudinal and transversal dispersivities. So these were 4 parameters plus another 10 parameters related to the potential releases of in 2 locations during 5 different time steps. So this will be the 14 parameters that the artificial network is trained, and later is used to basically identify those 14 values from data collected in the aquifer. As I said, this is the first one, and it will not be the last, because there will be many papers coming later that basically use the same approaches. In 2012, we had this Markov chain Monte Carlo and application of surrogate models by Zheng and others. The interesting thing is that in a way it's an extension of the geostatistical approach. The geostatistical approach is a Bayesian approach in that we are seeking the posterior distribution of the parameters given the data. And what happens is that when the forward model is linear, you can explicitly compute this posterior distribution, and that's what Scotgrass and Kitanidis do. They actually compute those posterior distribution and the moments, basically the expected values of those moments that will give me the best estimate of my model parameters. So this was done in the geostatistical approach. I mean, but you know that at some point there will be a depart from this linearity, and there will be a need to actually sample this posterior distribution, for which we will not have the exact expression. And that's what Zheng et al. Did. It's sampling the posterior distribution of obtained with the Bayes equation using Markov chain Monte Carlo approach, and because the Markov chain Monte Carlo approach requires many evaluations of the forward problems, they also propose to use surrogate models in order to get the values of the forward model in a fast way without having to run it as so many times. The way they propose in this particular case is what is called grid interpolation, in which basically you evaluate your forward model on a grid, and this grid basically in each point you have a collection of the parameters that describe your problem, and what happens is when you are trying to evaluate the forward model for a point that is not in the grid, so a collection of those parameters that is not in the grid, what you will do is an interpolation from the values in the grid using some interpolation functions that they explain how to compute in the paper. It's also interesting that they also address the problem of the identification of the location, the actual XY coordinates of the source. Next, in 2018, my group decided to get into this problem with already with an idea of trying to develop something that would be closer to reality. And for the first time, there is a work that actually addressed the problem of identifying the contaminant source parameters and also the underlying heterogeneous hydraulic conductivity. We use these reference cases, this aquifer with some kind of a channelized heterogeneity within channels with high conductivity and areas with low conductivity. We address 2 problems in which the injection happens in a high conductivity area and also in a low conductivity area, and we were successfully capable to identify both the underlying hydraulic conductivity distribution, but also the parameters that describe the concentration, the contaminant source injection, basically the XY locations, which require some specific analysis, modifications of the ensemble-Kalman filter to do it, the initial release of the contamination, the final release, and the strength of the release. is still, I mean, it uses a stochastic framework. This is a Kamal filter, so you get not only an estimate of the parameters, but also of the uncertainty around this estimation. And is, as I said, is capable of identifying a completely heterogeneous spatial distribution of the conductivities. Truth is that all the other parameters related to flow and transport, like boundary conditions or porosities or dispersivities, are perfectly known, which leaves us not exactly, I mean, in a real conditions in which you will not know those parameters either. In summary, between this 1998 and 2021, there were many papers published, but most of them were focused on the mathematical problem of the solution of this optimization formulation. And you will find machine learning approaches, many heuristic, Markov chain Monte Carlo, hybrid approaches, but very few of the applications actually think on the possible applicability of these to real forensic cases in which you need to find out who actually produced the contamination that is being seen on your observation wells. I would say there is these papers basically show incremental research. I mean, the typical that you are trying just to get a new heuristic approach to solve the optimization problem, or make hybrid approaches. I mean, it's basically going always around the same problem of solving the optimization problem, forgetting about the fact that you want to apply this to a real case. There has been very few advances into application of real applications. There are very few applications to real cases in practice, I mean, published. And that's part, I mean, this frustration that I mentioned before that I have. So which are the issues which should be solved? First of all, the one of dimensionality. I mean, you have here a histogram of the papers that have been published. I mean, a distribution of the paper that I have already shown you, categorized by the dimensionality of the problem. It's incredible that it's still today. I mean, there are many people who are doing one-dimensional problems, who are solving one-dimensional problems. Three-dimensionality. I mean, some of the papers, especially in the later years, have been used three-dimensional modeling, but still most of the papers that are being published are in 2D. So if we want to get closer to reality, we have to realize that flow and transport in an aquifer is three-dimensional, and we have to make sure that our methods do work in three-dimensional cases. The issue of the source. I mean, the source. I always say that it would be impossible to try to find an unknown number of sources working during an unknown time with unknown strengths. That's a very difficult problem to solve. It's a very difficult problem to formulate, and it's a very difficult problem to solve. So there is a need to have some kind of prior knowledge if we want to identify. Maybe you know how many sources there are. Maybe you know, I mean, which are the potential locations for the sources. But there is a need to have some information, prior information, to solve the problem. I mean, the most generic case of unknown number of unknown contaminant sources acting during an unknown period, it's very difficult. And much less if the source is distributed in space. I mean, very few papers address the problem of what happens if your source is not a point source. I mean, you have some kind of source arising from a large volume or from a large area of contamination. Some papers have been published, but they always use a very simplified geometry in order to get it. Real applications. There are very few real applications. There are a few laboratory experiments and a few demonstrations on laboratory experiments. Very few applications. The data is very difficult to get. Truth is that when you are dealing with these contamination problems, maybe, I mean, the data is difficult to get because it's proprietary, and whoever has the information doesn't want to release it. So yeah, that's an additional problem. It's difficult to get real data in which to test all these approaches. But the main problem, the largest problem, is you need to account for uncertainties that goes beyond the uncertainty about which is the location of your contaminant and which are the strengths of the contaminations, like accounting for uncertainties on the processes. Sometimes, I mean, the evolution of the solute in the aquifer is not just it's not just a non-reactive. I mean, you have to account for reactivity or for some kind of absorption. I mean, you have to make sure that all the processes that are affecting your flow and transport are accounted for. The parameters, uncertainty about the parameters have to be accounted for. I have shown you some, a specific paper in which hydraulic conductivity heterogeneity has been considered, but it's not the only parameter that has to be addressed. I mean, you have other parameters like porosities and dispersivities and other ones, and also what has to do with the geometry of the site, with the boundary conditions, with external stresses that sometimes we give for granted that we know which are the values, and many times we do not know it. And also just try to, sometimes it's good to try different scenarios with different basically conceptual models to do the analysis. In most of the papers that I have shown you, the data acquisition is almost perfect, in the sense that you have a very large network of sampling locations from which to get the information to use in the inverse probleming. It's interesting, it's important to test more realistic networks, and it's also interesting to develop techniques that will explain how to deploy a network after the contamination has been detected. I mean, in principle, I may not have any observation locations. I may only have my well where I find out that there is a contamination, and then once I find out that contamination, is there an optimal way to deploy a network, an observation network that will allow me to identify the source and being as economical as possible and as minimal in number of observation as possible? That would be a very interesting additional work to perform. My frustration, as I mentioned at the beginning, is that there has been a big rush of papers on the subject in the last few years, and most of them, in my understanding, have basically introduced incremental research without keeping in mind that you have to solve at the end a problem that you would like to be able to apply it into real cases, into real forensic hydrogeology. My question, and I think it not only applies to this specific subject matter, is are we focusing only on what we know how to solve and forgetting the purpose of our models? Are we just basically trying to solve what we know how to solve? And as I said, just forget that your model, eventually you would like to apply them into real cases, and maybe there are many additional issues, additional features that have to be accounted for in the solution of your problem, that are basically being disregarded because most people are not accounting for them. I mean, it's like this driving of this inertial publication in which you are just trying to improve what someone else did, but narrowing the focus of your research. So with this, I finish my presentation of this short history about contaminant source identification in aquifers. I hope that you enjoyed, and I'm open for any question that you may have. Thanks very much.